In this video series, we will be discussing how to solve Newton's second law problems. Here is our first problem. Please pause the video and try to solve this problem. Okay, and now we will discuss the solution to this problem together. Now, the first step for solving this physics problem is to choose a problem-solving framework. The first two problem-solving frameworks that you encounter in your physics course are kinematics, which includes projectile motion, and Newton's second law. Which of those frameworks applies here? Well, we decide what problem-solving framework to apply by examining the concepts that are mentioned in the problem. This problem mentions a 3-kilogram block. That's a mass, and mass is a concept that fits into Newton's second law. The problem also mentions tension, which is a force, and force is a concept that fits into Newton's second law. This part of the problem mentions the normal force, and again, forces fit into Newton's second law. And this part of the problem mentions acceleration, which is another concept that fits into Newton's second law. So it appears we should use the Newton second law framework. Now, it's true that the concept of acceleration could also fit into a kinematics framework, but there are no other concepts in this problem that fit easily into kinematics, so it looks like we're just going to use the Newton's second law framework for solving this problem. So we used the concepts that were mentioned in the problem to decide what problem-solving framework to apply. We're going to apply the Newton's second law framework. It's important to attack Newton's second law problems systematically. So here is a handout that contains a systematic step-by-step process for attacking Newton's second law problems. So you should now pause the video and go to the video description box and click the link for this handout, and please print out this handout. You should have this handout in front of you while you're watching the video and while you're attempting to solve the remaining problems in this series. Now, the first step of the process is to make a sketch of the object. Now, this problem, like many problems, already provides us with the sketch. But something that we can add to this sketch is the velocity vector. It'll be helpful to add the velocity vector to this sketch. The direction of the velocity vector indicates the object's direction of motion. And if we read this problem carefully and study the diagram, I think that the problem implies that the block is moving to the right. From the way the rope is oriented in this sketch, it looks like the block is being pulled to the right along the table by the rope. Therefore, the velocity vector should point to the right. Here I've drawn that velocity vector pointing to the right. Now, whenever you draw a vector arrow, it's important to always label that arrow. So this arrow should get labeled as the arrow for the velocity vector. So we've completed this step. We were already given the sketch of the object, but we added the velocity vector to the sketch, keeping in mind that the direction of the velocity indicates the object's direction of motion. Now we're ready to move on to our next step, where we try to identify the question with a question mark and a symbol. So we're going to start by working on part A. Part A is asking us for the magnitude and direction of the normal force. You should know that force is a vector, and you should know that vectors are concepts that have a magnitude and a direction. And part A is asking for both the magnitude and the direction of the normal force. Do you know what a magnitude is? You need to know that a magnitude is a number that can be either positive or zero, but that can never be negative. So let's write down a question mark, and let's try to write down a symbol for what part A is asking us. Well, what's a good symbol for the magnitude of the normal force? A good symbol for the magnitude of the normal force will be lowercase n. Now, always try to use the exact right symbol. we don't want to use this symbol for the magnitude of the normal force, because if we write the arrow above the symbol, that indicates the complete normal force vector, which would include both a magnitude and a direction. The correct symbol to just show the magnitude is the lowercase n without the arrow. With the arrow indicates the complete vector, magnitude, and direction. Without the arrow indicates just the magnitude. Now, part A is also asking us for the direction, so we can write that down as a separate part of the question. Here's a good way to write out that the question is asking us for the direction of the normal force vector. Now, in this case, we should use the arrow, because here we're thinking about a concept that has a direction. This would not be a good symbol to use in this line, because magnitudes don't have directions. Only the complete vector has a direction. So we've written down a question mark, and then we represented the question with a symbol or with a combination of words and a symbol. I encourage you to actually write down for each problem a question mark and write down the symbol or words in a symbol that represents exactly what the question is asking you for. So we've completed this step of identifying the question. Now we'll move on to check that the units are SI units. You should know that SI units are the standard units that we typically want to plug into our physics equations. Well, kilograms are the SI unit for mass, and newtons are the SI units for force. You need to memorize what the SI units are for each concept. These are the correct SI units. So we completed this step. We checked that the given units were indeed SI units. Now, this next step is not applicable to this problem. This step is for symbolic problems, but the problem that we're working on now is numeric. So we can skip this step. And now we're ready to move on to our free body diagram. We want to identify the object that we're going to apply Newton's second law to, and that's going to be the object whose mass is mentioned in the problem. Well, the problem mentioned the mass of the block. So we're going to apply Newton's second law to the block, and that means that our free body diagram is going to focus on the block. During what interval of time? Well, we're going to focus on this block during the interval of time during which the block is being pulled along the table by the rope. So we've completed this step. The object that we're going to apply Newton's second law to is the block during the interval of time during which it's being dragged along the table by the rope. We're ready to move on to the next step and start the free body diagram for the object. For which object? For the object that we just identified, the block. By the way, I hope that you will print out the problems document that accompanies this video series, so that you can keep examining the problem during all parts of this solution, even when the problem doesn't remain on the screen. And keep in mind that if you're finding that this video solution is moving too slowly, you can always use the solutions document as a replacement or a supplement to the video explanation. You should look in the video description box for all of these resources. Now we'll move to our next step and start the free body diagram. We're going to make a free body diagram showing all the forces being exerted on the block. So first of all, I'm going to draw a dot, and the dot represents the block. Now we begin the free body diagram by drawing a vector for the object's weight. What is the direction of the weight force? Well, you need to know that there is a simple rule for figuring out the direction of the object's weight. So now we're going to start using a second handout. This handout is a forces handout. So again, you should pause the video, go to the video description box, click on the link for this forces handout, and print this out. This is another handout you should have printed out and in front of you while you're watching the videos. So you should have the Newton's second law, this Newton's second law handout printed out, and also hopefully now you have this forces handout printed out. Here's some general information about forces. A force is a push or a pull. Hopefully this is review for you. Every force is exerted by some object on another object. Forces are vectors, which means they have directions and can be broken into components. A magnitude, a general symbol for the magnitude of the force would be capital F, and we've already discussed that the SI units for force are newtons. These are all facts that you should have memorized about forces. Now here's some stuff that you need to know about weight forces. What is the weight force? The weight force on an object is the gravitational force exerted by the Earth on the object. All the objects in standard problems experience a weight force. And remember I said there was a simple rule for figuring out the direction of the weight force? Well, I hope that you agree that this rule is simple. The direction of the weight force is down. This should make sense to you. Remember that the weight force comes from the Earth's gravity. And I think it should match your common sense that gravity is a downward pulling force. So we can draw the weight force pointing down in our free body diagram. The weight force points down. Remember to label every vector arrow that you write down. Here's the symbol to indicate that this is the weight force. Remember, always try to use the exact right symbol. Now, your textbook and your professor might use a different symbol for the weight force. Your textbook or your professor might use this symbol. This symbol stands for gravitational force. Well, remember that the weight force is the gravitational force exerted by the Earth on an object. So you can see why this symbol for gravitational force is logical. This symbol is perfectly fine, but I prefer to just use W just to cut down on the number of subscripts that you need to use. So in these videos, I will use W rather than the F sub G symbol. But you should remember, I hope you should remember, that the weight force is the gravitational force exerted by the Earth on the object. You should use a lowercase w here. Don't use capital W because we'll use that for other concepts later in the course. You need to memorize these key facts about the weight force. The weight force on an object is the gravitational force exerted by the Earth on the object. You should memorize that the direction of the weight force is down. And you should know that all objects near the Earth or near an astronomical body experience a weight force. So for the types of problems that we're working on here, there will always be a weight force in your free body diagram. So notice you'll always complete this step of drawing a vector for the object's weight in the free body diagram. Now we will move on to the next step. To continue the free body diagram, we have to ask what is touching the object. What is touching the object? All the other forces in the free body diagram will come from things that are touching the object. Well, let's see. We know here that the block is being pulled along a table, so the table is touching the block. Since the table is touching the block, the table will exert a force on the block. How should we think about that? Well, the table is what we would consider a surface, and the force exerted by a surface is what's called a normal force. So we need to include the normal force in our free body diagram, the normal force that's exerted by the table on the block. Going back to our forces handout, here's the key facts that you need to know about the normal force. The normal force on an object is a force exerted by a surface on an object. Now, what is a surface? I don't think I'll try to give you a technical definition of a surface, but I hope you can recognize a surface when you see it in the problem. Some typical surfaces. In this problem, we're using the table as a surface, but I hope that you can see that a floor or a wall or an inclined plane could also be considered a surface that is touching the object. Now, in our free body diagram, we need to know what direction the normal force is pointing. Well, just like with the weight, there is a rule that tells us the direction of the normal force. Here's the rule for the direction of the normal force. The normal force points perpendicular to and away from the surface that is touching the object. The normal force points perpendicular to and away from the surface that is touching the object. Well, the block here is on top of the table. So perpendicular to the table would be a vertical line, and pointing away from the surface of the table would point up. So the normal force in this case points up. So we need to add that vector to our free body diagram. Here's our vector for the normal force, pointing up. And remember, every vector arrow that you draw has to be labeled. The label here would be N for normal force. In your textbook, you might see this symbol used for the normal force, or you might see this symbol used for the normal force. But I'm going to use lowercase n. I prefer not to use this symbol because, again, this symbol allows us to use one fewer subscript. And I prefer not to use a capital N for the normal force because capital N we already know stands for newtons. Since we're using capital N for newtons, I think it's better to use lowercase n for normal force. So you might see these two symbols in your textbook are used by your professor. But in these videos, I will use the symbol lowercase n for normal force. Always try to be careful with your symbols and use the exact appropriate symbol in each part of your solution. How did we know that this normal force points up? Because that's the direction that's perpendicular to and away from the surface of the table that is touching the block. Now, do not assume that the normal force points up in other problems. There are many situations where the normal force does point up, such as the problem that we're working on. But there are also many situations in which the normal force does not point up. So don't assume that the normal force points up. Instead, memorize this rule. The direction of the normal force is perpendicular to and away from the surface that is touching the object. Here's that rule to memorize. Notice, why is this called the normal force? Well, in mathematics and physics, normal is not used to mean ordinary. We're not using the word normal here to mean ordinary. In mathematics and physics, normal means perpendicular. That's the technical meaning of normal. So now it should be clear, this is called the normal force because it's a force that is perpendicular to the surface. Normal means perpendicular. Also to memorize that the normal force is a force exerted by a surface on an object. These are the typical types of surfaces that you'll see on the problems that you're working on. And you should keep in mind that the purpose of the normal force is to prevent the object from moving through the solid surface. The purpose of the normal force is to prevent the object from moving through the solid surface. And so it makes sense that this should be the direction of the normal force. On this problem, the weight force is trying to drag the block down through the surface of the table. And the normal force is going to prevent that from happening. And it should make sense to you that the way for the normal force to prevent the block from being dragged down through the surface of the table is for the normal force to point perpendicular to and away from the surface of the table, which in this problem happens to be up. So if you keep in mind that the purpose of the normal force is to prevent the object from moving through the solid surface, then it should make sense to you that the direction of the normal force is perpendicular to and away from the surface that is touching the object. Remember, memorize this rule for the direction of the normal force. Now, are there any other forces that we should include in our free body diagram? Well, follow our systematic process. Remember the forces, coming back to that normal force again for a second, you should keep in mind that any surface could possibly exert both a normal force and a frictional force. When there's a normal force, there could be a frictional force from the surface. We have to check that, but that won't apply on this problem. In this case, we know that there's no friction because the problem told us so. The problem told us that there is no friction. Anytime that you include a normal force in your free body diagram, you should check whether that same surface will exert a frictional force. But we know that on this problem, there's no friction. So now moving on, are there any other forces on the object? Well, remember that in this step, the only forces that can exist besides the weight are forces that are exerted by things that are touching the object. So simply ask yourself, is there anything else touching the block besides the table? Now we can see that Jessica's pulling the block by the rope. So we know that the rope is touching the block. The rope is touching the block, so the rope can exert a force on the block. How do we handle that force? Well, that force is what we would call a tension force. And here's some material from the forces handout about the tension force. So a tension force is a force exerted by a rope or other things that are analogous to ropes like strings or cord. The tension force is the force exerted by a rope on an object. At least this is the definition that I'm going to be using in these videos for tension. Now remember we saw there were rules for figuring out the direction of the weight force and the direction of the normal force. And there's also a rule for figuring out the direction of the tension force. The direction of the tension force is parallel to the rope and away from the object. I think that should make pretty good sense. So for example, in this case, the direction of the tension force would point in this direction. In this direction. This is the direction that's parallel to the rope and pointing away from the object. This direction should make good sense to you because your common sense should tell you that we use a rope to pull on the block. You can't use a rope to push on the block, only to pull. And if this rope is pulling the block, then it should make sense that the direction of that pulling force is in this direction, parallel to the rope and pulling away from where the block is located. So we need to include that force in our free body diagram. Here's the direction of the tension force, pointing in the direction we found that's parallel to the rope and pulling away from the block. Remember, every vector arrow you write down has to be labeled with a symbol. And the correct symbol for this vector arrow is capital T for tension. Try to use the exact right symbol. The symbol for tension is a capital T. Notice that it's best in the free body diagram to include these arrows. Leaving out these arrows would be not very good symbols, because remember that without the arrows, these stand just for the magnitudes, and magnitudes don't have a direction. Here we want to use a symbol for the complete vector, which includes its direction. So these are the best symbols to use in your free body diagram for the force vectors. Now, the purpose of the free body diagram is to show to identify all the forces on the object and to show the directions of the forces on the object. So to accurately show the direction of the tension force, we should include this reference line and this 60-degree angle, so that we're completely specifying what the direction of the tension force is. Notice that we draw this reference line as a dashed line to show that it does not represent a force. It's just included so that we can show the angle, the direction of the force accurately. So your free body diagram should include this 60-degree angle. The first time I recorded this video, I forgot to show this angle, so some of the parts of the rest of the video will leave the angle out. But it's best for your diagram to include that angle. I see students might have a tendency to think of this force from the rope as being another normal force. So notice that's not right. We don't consider the force exerted by a rope to be a normal force, because the rope is not considered a surface the same way the table is. I hope you can see how those are different. I'm not going to try to give you a formal definition of what we consider a surface that can exert a normal force, but I hope that this list of typical surfaces will give you a feel for what we mean by a surface. Typical surfaces are floors, tables, walls, inclined planes. I hope you can see that a rope is not the same type of thing as these surfaces. So the force exerted by the rope is not called a normal force. Instead, the name for that is tension force. You need to memorize these facts about the tension force. The tension force is the force exerted by a rope or a string or a cord, etc., on an object, and you need to memorize this rule for figuring out the direction of the tension force, parallel to the rope, pointing away from the object. Are there any other forces being exerted on this block? Are there any other forces on the block? Well, we should ask, is there anything else that is touching the block? And going back to the problem, reading carefully, we can see that there's nothing else that's touching this block. The only things touching the block are the table and the rope, and we've already included their forces. Since there's nothing else that's touching the block, there can't be anything else exerting a force on the block. Remember that aside from the object's weight, all the other forces come from things that are touching the object. Remember that every force is exerted by some object on another object. Every force is exerted by some object on another object. So why don't you pause the video and ask for each of these forces. For each of these forces is being exerted by who, on who. Try to pause the video and decide who is exerting each of these forces and who is the force being exerted on. Here's the answer to that question. Remember, the normal force is being exerted by the surface, by the table, on the block. The tension force is being exerted by the rope, on the block. And the weight force is being exerted by the earth, on the block. Remember that the weight force is unusual and weird because the weight force is usually the only force you see in the first semester that can be exerted by something that is not touching the object. The earth is not touching this block. The earth is not touching the block is on the table, not on the surface of the earth. But even though the earth is not touching the block directly, the earth can still exert this weight force on the block. How is that possible? It's possible because the weight force is gravitational. The weight force is the gravitational force exerted by the earth on the object, and gravity is a weird force that can act at a distance. Unlike the other forces that you'll see in the first semester, gravity is a weird force that can act at a distance, even when the earth is not touching the object. Okay, so keep in mind that the weight force is usually the only first semester force that can be exerted by something that is not touching the object. We split up the steps for the free body diagram into two separate steps. First, there's a step where we draw the vector for the object's weight. Every free body diagram will have a vector for the object's weight. Then we have a separate step for forces exerted by things that are touching the object. Because remember, aside from the object's weight, all the other forces in your free body diagram in the first semester will usually come from things that are touching the object. If something is not touching the object, it's not going to exert a force on the object. That's the rule that will generally work for first semester problems, aside from that force for the object's weight. Now, also remember that the free body diagram should include only the forces being exerted on the object, on the block. We shouldn't be including any of the forces exerted by the block. For example, we know that the table is going to be exerting a force on the block. Now, it's also true that the block will exert a force on the table. The block will exert a force on the table, but that does not get included in this free body diagram. We don't want to include any of the forces being exerted by the block. we only want to include in this diagram the forces being exerted on the block. It's a good idea as a beginner to actually write down a description like this for each free body diagram. For each free body diagram, you should actually write down your description of exactly which forces you're going to include in the free body diagram. You should model your scratch work on the scratch work that I'm demonstrating in this video. And this description of the forces in the free body diagram is a good thing to imitate in your own free body diagram. All right, so now we've finished our free body diagram. Again, try to model your scratch work on the scratch work I'm using. So try to draw your free body diagrams like this. Try to make them as neat and clean as possible, clearly showing the directions of all the forces on the object. Remember that this dot represents the object, which is the block in this case. Be sure to always remember to label all your vector arrows. This free body diagram is useless because the arrows are not labeled. Without labels, the diagram is almost useless. Remember to include a label for each vector arrow. Okay, so make sure that you memorize and study this two-step process for drawing the free body diagram. First, draw a vector for the object's weight. Then, complete the diagram by asking what are the things that are touching the object. Aside from the weight, for the first semester problems, all the other forces in the free body diagram should come from things that are touching the object. Completed this first main phase of the process, the free body diagram, and we can move on to the force table phase. Now is a good time to write down our axes for the problem. We usually want to choose an axis that points in the object's direction of motion. We decided this object was moving to the right, so I'll write down a positive x-axis pointing to the right. Are our axes, and of course they should be labeled. I chose this as the positive x direction because that's the direction that the object is moving. And then I chose up to be a positive direction because that's a fairly conventional positive direction. If you have nothing better to do for the y-axis, it's also conventional when you have a horizontal and vertical axis to call the horizontal axis x and the vertical axis y. So that's what I did here. Do not assume that your axes should always be horizontal and vertical. There are many problems where the axes should be horizontal and vertical, like the problem that we're working on. But there's also many problems where the axes should be slanted, like this. So the rule is that it's usually best to choose your axes so that one of the axes points in the object's direction of motion, regardless of whether that direction happens to be horizontal or vertical or slanted. So we've completed this step. Make sure that you actually write down the axes. And usually you should choose an axis that points in the object's direction of motion. All right, now we're going to begin our force table. Here's our setup for the force table. Notice that there are 3 rows in the force table. The first row of the force table is where we enter the magnitudes of the overall vectors. And the second and third rows of the force table are where we enter the components of the vectors. So notice that our free body diagram represents the directions of the overall vectors. The first row of the force table represents the magnitudes of the overall vectors. And then these 2 rows of the force table represent the components of the force vectors. Make sure that you use the exact right symbols in each part of the force table. Do you see why these are the exact right symbols for the magnitudes of the overall vectors in the first row? We would not want to use this symbol, or this symbol, or this symbol in the first row, because these are the symbols for the complete vectors, including a direction. Instead, we want to use the symbols in the first row without arrows to indicate that these represent just the magnitudes of the overall vectors. And then, of course, we use x and y subscripts to indicate our x and y components in the next two rows. Make sure you try to use the exact right symbol at each part of the force table. This first row of the force table again focuses on the magnitudes of the overall vectors. So remember, a magnitude is a number that can be positive or zero, but that cannot be negative. So let's get started filling out the force table. Our first job is to determine how we're going to represent the magnitude of the overall weight force. Well, were we given a value for the magnitude of the weight force? No, we were not given a value for the magnitude of the weight force. Many forces have some forces have special formulas that can represent the magnitude. Is there a special formula for the magnitude of the weight force? And the answer is yes. The weight force is a force that has a special formula for its magnitude. Here's the special formula for the magnitude of the weight force. We can also see that in this handout. There is a special formula for the magnitude of the weight force. Here's the special formula, W equals mg, for the magnitude of the weight force. So we'll use this formula to represent the magnitude of the weight force. This is the first time we've used this crucial formula, so let's pause and make sure we know exactly what each of these symbols stand for. You should actually pause the video now and make sure you know exactly what each of these symbols stand for. What does this symbol stand for? I hope you didn't say this stands for the weight force. This symbol stands for the magnitude of the weight force. This would be the symbol for the complete weight force, including its direction. Without the arrow, this is just the symbol for the magnitude. What does this stand for? Well, clearly this is the mass of the object. The mass of which object? The mass of the object that you're figuring out the weight of. And what does this symbol stand for? Many students have a bad habit they call little g gravity. But that's a bad habit. That's not a useful definition at all. So we should say that little g is the magnitude of the acceleration due to the Earth's gravity. Don't say that little g stands for gravity. Don't even say that little g stands for the acceleration due to gravity. We should say that little g stands for the magnitude of the acceleration due to the Earth's gravity. You should memorize that definition for little g. We'll be using this formula a lot, so we should ask, why does this formula make sense? Why does it make sense that the mass and little g affect the object's weight? Well, loosely speaking, we could say that an object's mass reflects how much material is in the object. The mass reflects how much stuff or material is in the object, loosely speaking. Well, I think it should make sense to you that objects that consist of more material have a greater weight. So it makes good sense that the mass is in this formula. Objects that have more material inside them have a greater mass, and it should make sense that that would cause a greater weight. So it makes sense that little m is in this formula. Now, why would this formula be affected by little g? That's a little bit more subtle. To understand why mass was in the formula, I compared two objects with different masses, and I saw that different masses should result in different weights. But how could you have different little g's? Little g is a constant, isn't it? Well, little g is a constant near the surface of the Earth, but if you went to a different planet, you would experience a different acceleration due to gravity. So you could imagine, for example, going to the moon. Now, the moon has weaker gravity than the Earth, and as a result, the moon would have a smaller little g. The moon would have a smaller magnitude of the acceleration due to gravity. And notice that the formula predicts then that objects on the moon will weigh less, which you might know is the truth. If you take an object to the moon, it will weigh less than it does on the Earth. And the formula would predict that because of the little g. If you take an object from the Earth to the moon, when you do the calculation on the moon, there will be weaker gravity, a smaller magnitude of the acceleration due to gravity, so a smaller little g, and the formula would predict that objects on the moon will weigh less than they do on the Earth. So when you follow that logic, it should make good sense that little g can affect the object's weight. On planets with weaker gravity, there's going to be a smaller little g, and as a result, things will weigh less. Now we've explained why this formula for the magnitude of the weight makes good sense. It makes good sense that the weight of an object would depend on the mass of the object and also on the little g for the planet where you're figuring out the weight. Of course, in almost all the problems that we'll be working on, we'll be using the little g for the surface of the Earth. Let's start plugging into this formula for this problem. What can we plug in for the mass? The mass was 3 kilograms. What do we plug in for little g? Well, you should know that little g near the surface of the Earth for the problems we'll be working on is 9.8 meters per second squared. So I'll plug in the number 9.8. Sometimes students think that they should plug in negative 9.8, but that's wrong. We don't include a negative here because remember little g stands for a magnitude, and magnitudes can never be negative. That's one reason why it's important to know that little g is a magnitude. That reminds us that we would never plug in negative 9.8 for little g. Little g is a magnitude, so we just plug in the positive number, 9.8. Let's do the calculation. 3 times 9.8. So we get that to be 29.4. Now, when you've solved an equation to a single number, you should always record the units for that number. All the units that we plugged into this formula were in SI units, so we can trust that this number comes out in SI units. What are the SI units for weight? Well, remember, weight is a force, and the SI units for force are newtons, so the units for weight are newtons. The SI units for weight are newtons. You should memorize that the SI units for weight, just like the SI units for all other forces, are newtons. My recommendation is that when you plug numbers into the equation, you can leave the units out, just to make the math simpler. But then when you've finished solving an equation to a single number, you should always put the units back in. You should write the general equation before you plug in specific numbers. First here I wrote the general equation, then I plugged in some specific numbers. Now we can put this number in our force table. The magnitude of the weight is 29.4 newtons. Notice that you should do all of these calculations off to the side. Don't do these calculations in the force table. Save the force table for the final results to keep the force table neat. Now we need to break this weight force into components. How do we do that? Well, notice that our weight force is anti-parallel to the y-axis. Do you see why I call it anti-parallel? I say the weight is anti-parallel to the y-axis because they point in opposite directions. Well, here's the method for when vectors are parallel or anti-parallel to one of the axes. Since the weight is anti-parallel to the y-axis, that means that the y component has the same magnitude and direction as the overall vector. Well, our overall vector points down, so the y component points down, which is our negative y direction. And the y component has the same magnitude as the overall vector. The overall vector has a magnitude of 29.4 newtons, so the y component has a magnitude of 29.4 newtons. And then the component for the other axis, the x-axis, is 0. This is the method when a vector is parallel or anti-parallel to one of the axes. Since the weight was anti-parallel to the y-axis, the component for the y-axis pointed down with magnitude 29.4 newtons, just like the overall vector, and down was our negative direction. And then the component for the other axis, the x-axis, was 0. This is the rule. Notice that there's no need to draw a right triangle to break this force into components. We can just use this simple rule. Well, we've completed the force table for the weight force, so now let's move on to the normal force. First, we have to make an entry to represent the magnitude of the normal force. How do we do that? Well, were we given a value for the magnitude of the normal force? No, we were not given a value for the magnitude of the normal force. Is there a special formula that represents the magnitude of the normal force? No, there's no special formula for magnitudes of normal force. In that case, we just represent the magnitude with a symbol. We just represent that magnitude with a symbol. And we've already written that symbol down. The symbol for the magnitude of the normal force is just lowercase n. So that's all there is to it. We're just going to represent the magnitude of this normal force with a lowercase n. You should memorize that there is no special formula for the magnitude of the normal force, and therefore we just represent the magnitude of the normal force with a lowercase n. So we're done with this row for the normal force. It makes some students uncomfortable that they don't have a number for this magnitude, but we'll see that that won't hinder us from continuing with the force table. So now we need to break that normal force into components. Well, notice that the normal force is parallel to, we can see that the normal force is parallel to our y-axis. I say that the normal force is parallel to the y-axis because they're pointing in the same direction. They're both pointing up. Since the normal force is parallel to the y-axis, the normal force has the same the y component will have the same magnitude and direction as the overall vector. Well, the overall vector points up, which is our positive y direction. And the magnitude of the overall vector, remember we're representing that magnitude of the overall vector just by the symbol lowercase n. So now we've shown that the y component has the same direction and magnitude as the overall vector, up, positive y direction, magnitude n. And in that case, when the vector is parallel to the y-axis, that means the component for the x-axis will be 0. So here again, we've illustrated this method for breaking a vector into components when the vector is parallel or anti-parallel to one of the axes. Many students have difficulty dealing with the normal force and breaking it into components because it makes them uncomfortable that they don't know a number for the magnitude. So I hope that you can see that we don't need to know a number. If you don't know the number for the magnitude of a force, you just handle it like this. You represent the magnitude of that force with a symbol, and then you use that symbol to help you represent the components. It might seem odd to you that we included a plus sign here because, after all, usually in mathematics, we don't usually include plus signs in front of positive numbers in mathematics. But I would recommend that as a beginner in physics, you should definitely include a plus sign in front of positive components. You should include a plus sign in front of positive components. There's two advantages to that. One advantage of the plus sign is that it reminds you of the importance and meaning of the sign. The plus sign recommends us that this y component points up our positive y directions. There's an important meaning to that plus sign. Also, remember that one of the most common mistakes that students might make on this problem is forgetting the negative sign in front of w sub y. Well, if you force yourself to always include a plus sign in front of your positive components, you are more likely to remember the negative signs that you need in front of your negative components. You probably won't see your professor or textbook including a plus sign in front of positive components, but I recommend that that's a habit that you should follow as a beginner in physics. It will help you to have a deeper understanding of what the component means, and also will help you to avoid mistakes like leaving out negative signs in front of the negative components. All right, so now we've finished the entries for the normal force in our force table. Remember, again, we saw what to do when when you don't know a number for the magnitude. If you don't know a number for the magnitude, you just represent that magnitude with a symbol, and you can use that symbol to represent the components. Notice that when we were working with the normal force in the force table, we did not try to figure out how the normal force would interact with the weight and the tension. We did not, in the force table, try to figure out how the normal force will interact with the weight and the tension. The normal force will be affected by the weight and the tension, but it's not our job in the force table to figure out that relationship. Instead, we just represent the unknown magnitude of the force table by this symbol without worrying about how it will be affected by the other forces. Later in our solution, the Newton's second law equations will figure out for us how the normal force will be affected by the weight and the tension. We don't have to figure out how the normal force will interact with the weight and the tension in the force table, because the Newton's second law equations will figure out that relationship for us later in our solution. So rather than trying to figure out how the normal force is affected by the weight and the tension, we simply represent it. We simply represent its unknown magnitude by this symbol, little n. For purposes of filling out the force table, do not try to figure out how the forces will interact with each other. Newton's second law will figure out those relationships for you later in your solution. Now we're ready to move on to the tension force. We need to represent the tension. We need to represent the magnitude of the tension now in this row. Well, ask yourself, were you given a value for the magnitude of the tension? And actually we were. We were given a value for the magnitude of the tension, 15 newtons. The problem says that the tension in the rope is 15 newtons, and we can interpret that as meaning that the magnitude of the tension in the rope is 15 newtons. This wording is used to really mean that the magnitude of the tension in the rope is 15 newtons. Notice that it's important to keep going back and rereading the problem. You might have forgotten that this problem gave you this number, so keep going back and restudying the problem to make sure you're using all the necessary numbers. So we'll write down that the magnitude of the tension is 15 newtons. When you're given a value for the magnitude, you can just use that value for the magnitude. By the way, you should keep in mind that there is no special formula for the magnitude of the tension. There's no special formula for the magnitude of the tension force. In this case, though, we were given a number for that magnitude. Now we need to break this tension force into components, and I hope you can see that we will not use this method, because the tension is neither parallel nor anti-parallel to either of the axes. Our tension force is neither parallel nor anti-parallel to the x or y axis. The tension force is at an angle to both of the axes. So this method is not appropriate. What's the correct way to break the tension into components then? Well, in this case, we have to draw a right triangle. We have to draw a right triangle in order to break this tension force into components. I discussed in detail how to break a vector into components in my previous video series on vector components. And you can find a link to that previous video series in the video description box. In this case, we have to draw a right triangle. We have to draw a right triangle in order to break this tension force into components. We're not going to draw that right triangle in our free body diagram, because we want to keep the free body diagram neat and clean. So we'll draw a separate sketch where we draw the right triangle that we'll use to break the tension force into components. So we've recopied the overall tension vector with its angle, and now we have to draw that right triangle. Here's the method for drawing the right triangle. We want the overall vector to represent the hypotenuse. So this line will represent the hypotenuse. Then we draw one leg of the triangle parallel to the x-axis. So through this point, I'll draw a line parallel to the x-axis. Here's that line parallel to the x-axis. It overlaps with our dashed reference line. And then the other leg of the triangle should be parallel to the y-axis. So through the head of the overall vector, I'm going to draw a line, a vertical line, parallel to the y-axis. So that's the method for drawing the right triangle. The overall vector should be the hypotenuse. One leg should be parallel to the x-axis, and one leg should be parallel to the y-axis. Of course, we could draw a different right triangle. Here we drew a right triangle below the overall vector. We could have drawn the right triangle above the overall vector, but then it wouldn't include the 60-degree angle that we were given. So in this case, it's better to draw the right triangle below the overall vector to include the 60-degree angle that we were given. Now, in this problem, the legs happened to come out horizontal and vertical because our axes were horizontal and vertical. But do not assume that the legs of your right triangle will always be horizontal and vertical. On many problems, the legs will be horizontal and vertical because on many problems your axes will be horizontal and vertical. But there are also many problems where the legs are not horizontal and vertical because you will later see many problems where you do not use horizontal and vertical axes. So don't assume that the legs will be horizontal and vertical. Instead, just make sure that one leg is parallel to the x-axis and one leg is parallel to the y-axis, however you might have drawn your axes. Now, I hope you're familiar with the idea that this end of this vector is called the head of the overall vector, and this is called the tail. This is a head of a vector, and this is a tail. Well, we need to draw heads and tails on the components now. The simplest way to figure out the directions of the components is to say that our overall vector points up and to the right, and therefore the components should point up and to the right. I've drawn arrowheads to show that the components are pointing up and to the right because they represent the overall vector, which points up and to the right. Now, here's a more formal way to figure out those directions. The rule is that because the components represent the overall vector, the head of a component arrow should be at the head of the overall vector. Well, I got that here. Where we have the head of the overall vector, that overlaps with the head of the component. And the tail of the component arrow should be at the tail of the overall vector. And we have that here. Since this is the tail of the overall vector, I made that into the tail of this component, and therefore this is the head of that component. So the more formal way to determine the directions of the components is that the head of the component should overlap with the head of the overall vector, and the tail of the component should overlap with the tail of the overall vector. You should memorize these rules for drawing the sides of the right triangle, and these rules for drawing the directions of these components. Now remember that we always want to label every vector arrow that we draw. Notice that components have directions, so components are also vectors. Well, the correct labels here are, this should be labeled T sub x, because this is the x component of the tension, and this should be labeled T sub y because it's the y component. This leg is parallel to the x-axis, which makes it the x component. This leg is parallel to the y-axis, which makes it the y component. Always try to use the exact right symbol at each point in your work. Now we have to determine values for these components. And I think we've already seen that each component has two parts. It has a sign and it has a magnitude. And we're going to figure out those two parts separately. I suggest that you should figure out the sign of the component before you figure out the magnitude. So let's figure out the signs of these components. That's straightforward. The x component points to the right, which is our positive x direction, and therefore T sub x is positive. The y component points up, which is our positive y direction, and therefore the y component in this problem is also positive. Now you can see why it was so important to put the arrows on these legs. Without these arrows on the triangle legs, we wouldn't be able to figure out the directions of the components. Remember that I've suggested that it's a good idea to include plus signs in front of your positive components so that you'll notice when components are negative. Now that we've figured out the signs on these components, we can go on to figure out the magnitudes of the components using SOHCAHTOA. By the way, the first time I recorded this video, I forgot to figure out the signs of the components before working on the magnitudes. So you'll see these plus signs disappear in the next part of the video, but it is best to figure out the signs before you work out the magnitudes, because otherwise you might forget to figure out the signs at all. Now we want to apply the memory aid SOHCAHTOA, which I hope you're already familiar with. So we need to label the hypotenuse, opposite, and adjacent sides in this right triangle. Which side is the hypotenuse? This side is the hypotenuse. Why? Because it's opposite to the 90-degree angle. Now, in order to know the opposite and adjacent, we have to decide which of these acute angles we're focusing on. Are we focusing on the 60-degree angle or the acute angle at the top of the triangle? Well, the convention is to focus on the angle that you were given. Since we were given the 60 degrees, I'm going to focus on that 60-degree angle, so I'll put in an asterisk to remind myself that we're focusing on this 60-degree angle. If you wanted to, you could focus on this angle at the top of the triangle, but it's more conventional to focus on the angle that you were given. Now, what does opposite and adjacent mean? Opposite and adjacent means opposite, the legs that are opposite and adjacent to the angle with the asterisk that we're focusing on. So we should say this leg is adjacent. Adjacent to who? Adjacent to the 60-degree angle that we're focusing on. And we should say that this leg is opposite. Opposite to who? Opposite to the 60-degree angle that we're focusing on. So I hope you can see why this asterisk is important. I hope you can see that if we had chosen to focus on this top angle, then the side which was opposite and the side which was adjacent would have flipped. Who is opposite and who's adjacent depends on which angle you're focusing on. If we had focused on this angle, there would be a different side that would be labeled adjacent and a different side that's labeled as opposite. You always need to identify which angle you're focusing on in the triangle. It's good to label that with an asterisk because which leg is opposite and which side is adjacent depends on what angle you're focusing on. Now I can build a little bit more into this triangle here. We know that the magnitude of the overall tension is 15 newtons. The magnitude of the overall tension is 15 newtons. Well, remember that this hypotenuse represents that overall vector. And the magnitude represents the length of the overall vector. So I should build that 15 newtons into the sketch. Notice that now I'm using the symbol T without the arrow because this now represents just the magnitude, and the symbol without the arrow represents the magnitude. Now, what should we use when we're setting up our SOHCAHTOA equations? Should we use sine, cosine, or tangent? Well, we'd like to have equations that include the hypotenuse, so we can include our 15 newtons number. So we should use sine and cosine because those equations include the hypotenuse. We should not, in this problem, use the equation for tangent because the equation for tangent would not let us plug in our number for the hypotenuse. So this memory aid SO means that the sine of the angle that we're focusing on equals the length of the opposite side divided by the length of the hypotenuse. Sine equals opposite over hypotenuse. So, and this memory aid tells us that the cosine of the angle that we're focusing on equals the length of the adjacent side divided by the length of the hypotenuse. K stands for cosine equals adjacent over hypotenuse. Make sure you include the angle. Without the angle, the equation would be meaningless. And now we can start plugging in. Well, the length of the opposite side will be represented by the magnitude of t sub y. And the length of the hypotenuse is 15 newtons. The length of the adjacent side will be represented by the magnitude of t sub x. And the length of the hypotenuse is 15 newtons. Now you might wonder why I used these absolute value signs. That's actually an important part of this process that I recommend that you imitate. Remember that this stands for the length of the opposite side, and this stands for the length of the adjacent side. Well, lengths can never be negative. So we need to use magnitudes here to represent the lengths, because magnitudes, remember, can also never be negative. It wouldn't make sense to represent a length with a component, because a length can never be negative and a component can be negative. So the component can't represent the length, only the magnitude of the component can represent the length. The purpose of these absolute value signs is to tell us that these SOHCAHTOA equations will not tell us the signs of the components. They won't tell us whether the components are positive or negative. They're only going to tell us the magnitudes of the components. We already figured out the signs of the components previously, and the purpose of the SOHCAHTOA equations now is to figure out the magnitudes. Now, on this problem, because the components both happen to be positive, you would kind of still get the right answer here, even if you left out the absolute value signs. But if one of the components were negative, it would be pretty important to include the absolute value signs here. So I recommend that you form the habit of using absolute value signs when you're determining on your components for the SOHCAHTOA equations, because the SOHCAHTOA equations only tell you the magnitudes of the components. They don't tell you the plus or minus signs. Okay, so now we can continue algebraically here. Hopefully you know that you solve this equation for the variable by multiplying both sides by the denominator 15. Because that way the 15s will cancel. And now both equations are solved for the magnitude of the component. Now we can use our calculator to do the calculation. So the first calculation is 15 times sine 60 degrees. This is in degrees, so make sure your calculator is in degrees mode. Make sure your calculator is in degrees mode. So I'll round that off. Well, the other one would be 15 cosine 60 degrees. All right, so I'll round this off, I guess, to 13. Now that we've solved to a single number, I'll put the units in. Remember that tension is a force, and the SI units for force are newtons. And Tx will be 7.5 newtons. So we followed this general strategy here of writing the general equations before we plugged in our specific numbers and symbols. As usual, we did not plug in units into the equation to keep the math simpler, but then we put the units back in when we solved the equation to a single number. Now these absolute value signs remind us that the SOHCAHTOA equations only tell us the magnitudes of the components. They don't tell us the plus or minus signs. So now I'm going to write another line where we will write the complete component, including the plus or minus sign. And we've already worked out that t sub y will be positive, and t sub x will be positive. We use absolute value signs in our SOHCAHTOA equations to remind ourselves that the SOHCAHTOA equations don't determine the plus or minus signs on the components. We need to determine the plus or minus signs ourselves in a separate step, like we did here. So we're trying to use the exact right symbol at each point. The exact right symbol here is absolute values to show that this line tells us only the magnitudes of the components. And the exact right symbol here is no absolute value signs because this line represents the complete component, including the plus or minus signs. Remember that I strongly encourage you to include plus signs in front of your positive components so that you'll remember to include negative signs in front of your negative components. Because both of the components happened to be positive on this problem, it wasn't crucial to be this careful with the absolute value signs and thinking about the signs. But there are many problems where some of the components will be negative, and so we should build good habits. Build the habits of using the notation that I've demonstrated here so that you'll be able to see when some of the components are negative. We'll illustrate that in some of the future videos in this series. Let's pause to ask if these components make sense by building them back into our triangle. So I've taken this number of 13 newtons and built it into the triangle as the y component. And I took the number of positive 7.5 newtons and built it into the triangle as the x component. And now we can use these rules to make sure that our components make sense. The longest side of a right triangle should be the hypotenuse. So let's check that this number is longer than the other two sides, and it is. 15 newtons is longer than the other two sides of 13 and 7.5. So that checks out. And here's a rule that you might not be familiar with, but in a triangle, longer sides should be opposite bigger angles. Well, I hope it's clear to you that this angle here at the bottom, the 60 degrees, this is the bigger of the acute angles, and this angle at the top here is the smaller. This is the smaller of the two acute angles. This angle is bigger than 45 degrees, so even without doing the calculation, it should be clear that this angle is smaller than 45 degrees. Well, notice here that our bigger angle is opposite the longer side of 13 newtons, and our smaller angle is opposite the shorter side of 7.5 newtons. So that also is consistent with this rule. That checks out. If either of these two rules had not matched our results, then we would have known that we had made a mistake. And we would know to go back and look for what our mistake was in figuring out the components. After you finish breaking the vectors into components, you should build those results back into your right triangle so that you can use these two rules to check if you made a mistake. The longest side of a right triangle should be the hypotenuse, and longer sides in triangles are opposite bigger angles. For the time being, when you're using SOHCAHTOA and breaking vectors into components, I encourage you to actually write out these steps. You might have skipped one or two steps of the algebra here, but otherwise I would recommend that you write each of these steps. Actually write down the right triangle, actually label hypotenuse opposite and adjacent side, and use that to set up the SOHCAHTOA equations. On this particular problem, we used cosine to figure out the x component, and we used sine to figure out the y component. But do not assume that you will always use cosine to find the x component and sine to find the y component. On many problems, you will use cosine for x and sine for y, like this problem. But there are many other problems where you might use cosine for the y component and sine for the x component. So rather than making an assumption, use the steps of the SOHCAHTOA process that we demonstrated here to determine the correct approach for each particular problem that you're working on. In addition, in this problem, we ended up multiplying by cosine and multiplying by sine. But there are some other situations where you use SOHCAHTOA where you might have to divide by sine or cosine. Again, use the steps of the SOHCAHTOA process to determine what the correct approach is for each particular problem, rather than assuming that a particular problem is going to be the same as the previous ones. Now remember, the goal for all that work was to take these numbers and build them into our force table. So let's do that now. Our Tx is positive 7.5 newtons. And our T sub y is positive 13 newtons. So now we've completed filling out our force table. So here's a summary of how to fill out the force table. If you're given a value for the magnitude of the force, then you use that value to represent the magnitude. That's what happened with the tension, where we were given the value of 15 newtons in the problem. Otherwise, if the force has a special formula for the magnitude, we use that special formula to calculate the magnitude. That's what happened for the weight, where we used the mg special formula to figure out the magnitude of the weight. And if there's no given value and no special formula, you simply represent the magnitude by a symbol. That's what we did for the normal force. We don't have a number for the normal force, and there's no special formula for the magnitude of the normal force, so we simply represented the magnitude of the normal force by the symbol n, and used that symbol to represent the components. Remember, for purposes of filling out your force table, we did not try to figure out how these three forces would interact with each other. We just thought about each force separately. The Newton's second law equations, later in our solution, will figure out the interactions between the forces for us. It's not our job to work that out in the force table. By the way, also keep in mind, what does this symbol stand for? I hope you didn't say this stands for the weight. This stands for the magnitude of the weight. What does this stand for? I hope you didn't say it stands for the normal force. It stands for the magnitude of the normal force. What does this symbol stand for? It doesn't stand for the tension. It stands for, the best way to put it is, the magnitude of the tension. Remember that these are the symbols that we would use for the complete weight, normal force, and tension force, including their directions. Without the arrows, the symbols remind us that this first row of the force table is for magnitudes of overall vectors. Then the next two rows are where you put the components. So try to imitate on your, you should make a force table for every Newton's second law problem, and you should try to make your force table imitate the notation and the setup that I used here. Notice that we tried to keep the force table, just like the free body diagram, as neat and clean and organized as possible. Ever any calculations or work that we had to do, like this, or like this, we did them off to the side. We just put our final results in the force table to keep it neat and clean and organized. Don't rush through the steps of making the free body diagram and the force table. Take your time when you're making the free body diagram and the force table, because if you make even one little mistake in the free body diagram or in the force table, the rest of your work will be useless and you will get the wrong answer. And if you do a good job on the free body diagram and the force table, then that will really set you up for a successful solution in the rest of your solution. So here's some ideas to memorize. Remember that you need to memorize that the magnitude of the weight force, well, you need to memorize that there is a special formula for the magnitude of the weight force. W, memorize the formula, or probably should memorize it, W equals mg, or at least have it on your cheat sheet. You should know it exists. You should memorize that there is no special formula for the magnitude of the normal force. We just represent the magnitude of the normal force by the symbol little n. And you should memorize that there is no special formula for the magnitude of the tension force. So here's the steps that we just completed. Again, if you're given a value, the first row of the table is the magnitudes of the overall vectors, and the next two rows are the components. If you're given a value for the magnitude, you use that value. Otherwise, if a force has a special formula, you use that special formula to represent the magnitude. And we saw that a force with a special formula is the weight, W equals mg. There's no special formula for normal force or for tension, and so if you have no special formula and no given value, you just represent the magnitude with a symbol, like we did for the normal force on this problem. The next two rows of the table are for the components. Remember, I strongly encourage you to always include a plus sign in front of all the positive components so that you'll remember the negative signs that you need in front of the negative components. Now, we do not include plus signs in this first row because the first row represents magnitudes. Magnitudes can never be negative, so there's no need to emphasize that they're positive. Components can be negative, so when a component is positive, we should emphasize that with a plus sign. And we use the value or the symbol for the overall magnitude that we'd already gotten in the first row of our table to calculate or represent the components. We used this number to help get the components, we used this number to help get the components, and we used this symbol to help represent the components. We're ready to proceed. So we finished the force table phase of our solution, and we're ready to proceed to the last phase, which is the Newton's second law equations. So I'm going to start by writing out the Newton's second law equations at the top of two adjacent columns. I've written the Newton's second law equations at the top of two adjacent columns. You should write down those Newton's second law equations so they look exactly the way I've written them here on the screen, using these exact symbols. Make sure to always use the exact right symbol in each part of your solution. Now, how do we start plugging into these? Do you know what this symbol means? Well, you should know that this symbol is called sigma. But what does it mean? It means add. This symbol means add. So this symbol means that we should add all the x components of the forces. So we need to add W sub x plus n sub x plus t sub x. And this symbol that we need means that we need to add all the y components of the forces. So here we need to add W sub y plus n sub y plus t sub y. So the sigma symbol means that we're adding the component forces on each side. Now we can start plugging in. So W sub x is 0, n sub x is 0, t sub x is 7.5. W sub y is negative 29.4. N sub y is n. T sub y is 13. So we've plugged in each of those forces. Remember that it's crucial to include this negative sign, or the equation will give you the wrong answer. On the other hand, I'm not plugging in separate pluses for the things that are positive. I'm not going to put in an extra plus sign just because that would overcomplicate the math. But it's certainly crucial to include this negative sign. Now, what can we plug in on the, well, I'll just point out then that we've now completed this step. And we've completed this step. On the left side of our Newton's second law equations, we added all the individual force components. Notice that we are adding, sigma means add. Sigma means add. So we're adding the force components, but some of the numbers we're adding include negative signs. Here's a number that we're adding, but it includes its negative sign. And of course, we got all those components from the force table. That's the reason why you have to do a good job on the force table before you can move on to the Newton's second law equations. Now in our next step, we should substitute into the right sides of our equations. Well, what can we plug in for the mass? That was given in the problem. It's a 3 kilogram mass. And now, what can we plug in for the accelerations? Oh, did I make a mistake here? I've been telling you always have to be careful to always use the exact right symbol. That includes the exact right subscript, so I can see that I got sloppy here. This should not be a sub x, should it? This is the y version of the equation, so sorry about that. Did you catch that mistake? That should have been a sub y. Try hard to always use the exact right symbol, including the exact right subscript. So I made a mistake about that. All right, now that's fixed. So what can we plug in here for a sub x? We'll have to reread the problem, but we really don't know what a sub x is. We don't know what a sub x is in this case. In fact, you can see that eventually the question's asking about the acceleration. Since we don't know the acceleration, what do we do when we don't know something? We just represent it by a symbol. So I'll just continue to represent that unknown by a sub x. Just like when we don't know the magnitude of the normal force, we just represent it by a symbol. When we don't know the magnitude, when we don't know the value of a sub x, we just represent that by a symbol. Now, is there anything that we can substitute for a sub y? Well, here's a mistake. I noticed that some students are tempted to substitute negative 9.8 meters per second squared for a sub y, but that would be a mistake in this problem. I can see why people would be tempted to do that, because this is this number that we use for a sub y in projectile motion problems. But this is not a projectile motion problem, so there's no reason to think that a sub y is negative 9.8 meters per second squared on this problem. For projectile motion problems, we do plug in negative 9.8 meters per second squared for a sub y. But for general Newton's second law problems, we generally do not plug in negative 9.8 meters per second squared for a sub y. And I hope you can see why. Negative 9.8 meters per second squared is the acceleration when the only force on an object is the force of the Earth's gravity. That is, negative 9.8 meters per second squared is the acceleration when the only force on the object is the force of the object's weight. But for Newton's, and that's the case for projectile motion problems. But for Newton's second law problems, there's generally a bunch of forces, not just the force of the object's weight. And therefore, for Newton's second law problems, there's no reason to assume that a sub y will equal negative 9.8 meters per second squared. So we won't make this substitution. This substitution would be a mistake for a Newton's second law problem. And of course, you would almost never see a situation where you would plug in negative 9.8 meters per second squared for a sub x in any type of problem. So keep in mind this important difference between how we handle projectile motion problems and how we handle Newton's second law problems. So we're not going to plug in negative 9.8 for a sub y, but in fact in this problem there is a specific number that we can plug in for a sub y. Is there anything we can substitute for a sub y? Yes, there is, because we know this object is moving horizontally. So we also know that the object is motionless vertically. The object is not moving at all vertically. That's implied by the problem and by common sense. The block is sliding horizontally on the table, so the block is vertically motionless. Well, if the block is vertically motionless, that means that its vertical acceleration is 0. So we can plug in the number 0 here for a sub y. Now, this is true, but I'd like you to pause and fill in this missing step. Why? When something is vertically motionless, why does that mean that its a sub y would be 0? It would be good to pause the video and see why this implies this. This might seem obvious to you, but actually velocity and acceleration are difficult and subtle concepts to work with. So let's take our time and really spell out the steps of this logic. Well, remember that the magnitude of v sub y would indicate the object's vertical speed. I hope you know that the magnitude of velocity indicates speed. Well, if the object is vertically motionless, then its vertical speed is 0. Since the block is vertically motionless, its vertical speed is 0. But this is not the reason that a sub y is 0, because there's no rule that a has to be 0 just because v is 0. There's no rule that this has to be 0 just because this is 0. But the key thing here is that v sub y is constant. At 0. If the block is vertically motionless, that means that v sub y is going to be 0 and stay constant at 0. And it's the fact that v sub y is constant that implies that a sub y is 0. Here's the rule that we're using. When the vy vector is constant during an interval, that's when the a sub y vector is 0. The acceleration tells you how the velocity is changing. So when the velocity is not changing, the acceleration is 0. Okay, so when the block is vertically motionless, that really does mean that the vertical acceleration is 0, but the logic and the thinking there is more complicated and subtle than you might have thought. Velocity and acceleration are difficult and subtle concepts. These rules in particular take a lot of practice for students to internalize. So we really can plug in 0 for a sub y. Notice that it would definitely be wrong to plug in 0 for a sub x. The object is not motionless in the x component, and there's no reason to think that the object is moving with constant speed in the x component, so there's no reason to think that a sub x is 0. Be careful to think about the two components of the acceleration separately. Our analysis for a sub y was completely different than our analysis for a sub x. Notice here that we followed this rule. We wrote the general equation before we plugged in specific numbers and symbols. Students make fewer mistakes and have better understanding when they write the general equation before they plug in the specific numbers and symbols. And we also followed this advice. Use the exact right symbols, including the exact right subscripts. Actually, I made a mistake with that at the beginning. Remember that at one point I had an incorrect X subscript over here, so I had to go back and fix that. So try hard to use the exact right symbols, including the exact right subscripts. For example, make sure that you write these general equations for Newton's second law exactly the same way that I have them on the screen. Do you see why these versions of the equations are bad and useless? Do you see why this would be a useless way to write these equations? First of all, this is useless because it doesn't distinguish between the two components. Notice that we saw that our analysis for a sub x was completely different than the analysis for a sub y. So it's crucial to label which equation is about the x components and which equation is about the y components, because you need to analyze those two components separately. And these are still not good versions of the equation, because when you write the equation this way, it makes it look like you're plugging in one force, x component on the left-hand side. We need to include the sigma symbol, because remember that sigma means add, to remind us that we're adding all the x components on the left side. And we need to include, by itself, this looks like we're only going to include one y component on the left side. We need to include the sigma here to remind us that we're adding all the y components on the left side. Write the Newton's second law equations exactly like this. And in general, always try to use the exact right symbols, including the exact right subscripts, in all of your work in physics. That's a key for improving your skills in physics. So we've completed this step. We substituted in the right side of the equation, substituting values and symbols for mass, for a sub x, and for a sub y. And we used this idea: when an object is motionless in a component, then that component of its acceleration is 0. On this problem, the object was motionless in the y component, and therefore the y component of its acceleration was 0. And we also explained the logic for why that is true. Now we can move on to our next step and use algebra to solve the equations. Let me just emphasize this number 0 a little bit more. This is something that a lot of students wouldn't get, which would prevent them from solving the problem, because notice the number 0 for a sub y was not directly given in the problem. There's nothing in the problem that directly states that a sub y is 0. So you need to be able to read the problem and visualize the situation and realize that because the object is moving horizontally, that implies that it is vertically motionless, and since it's vertically motionless, well, in this case, it's moving horizontally and vertically motionless, and that means that the vertical acceleration is 0. That's one of the keys to solving the problem. All right, so now we want to use algebra in these equations. Which equation should we work with first? Well, the question was asking about the normal force, and the normal force appears in the y equation, so it makes sense to work on this y equation. Notice that the y equation has one unknown. Since there's only one unknown, this is a good time to solve the equation. Notice again, if we hadn't been able to substitute for a sub y, then the equation would have two unknowns, and we wouldn't be able to solve it. So plugging in that number 0 for a sub y is definitely crucial for our solution. Well, we can rearrange this left-hand side. Simplify the right-hand side. We can always rearrange the order of an addition. So I rearranged the addition to put the two numbers next to each other. And now we need to add negative 29.4 plus 13. Negative 16.4. Whenever there's a negative sign in your equation, be extra careful to avoid making mistakes with that negative sign. Now to get the n by itself, we will add 16.4 to both sides of the equation. Why are we adding 16.4? To cancel out this negative sign. All right, now that we've solved the equation to a single number, we should put in units. When we plug numbers into the equation, we leave out the units to simplify the math. But then when you've solved to a single number, you should always put the units back in. Since all the units that we plugged in were in SI units, we can trust that the normal force will come out in SI units, and you should have memorized that because normal force is a force, its SI units are newtons. Let's ask if this result makes sense. First of all, did this come out positive or negative? And does that make sense? Well, mathematically, this result came out positive. Why does that make sense? Well, remember, this symbol does not stand for the normal force. This symbol stands for the magnitude of the normal force, and magnitudes can never be negative. So if the result had come out to be negative, we would have known we'd made a mistake. So it's a good sign that this magnitude came out to be positive. What about the size of this number? Does the size of this number make sense? Well, we can compare the magnitude of the weight. We can compare the magnitude of the normal force with the magnitude of the weight. So we have here 16.4 newtons is less than 29.4 newtons. So we have that the magnitude of the normal force came out to be less than the magnitude of the weight. Why does that make sense? You might want to pause the video and ask yourself, why does it make sense that the magnitude of the normal force came out to be less than the magnitude of the weight? Well, let's think about that in terms of our free body diagram. Now, this free body diagram will be more revealing if we think about the tension force in terms of its components. So do you see, here's an equivalent free body diagram where we showed the components of the tension. The tension points up and to the right. So the components of the tension point up and to the right. This will be the more useful version of our free body diagram for thinking about this relationship. Now, Why does the normal force exist? Keep in mind, as we've seen in this handout, the purpose, so to speak, of the normal force is to prevent an object from moving through a solid surface. The purpose of the normal force is to prevent an object from moving through a solid surface. So the purpose of the normal force in this problem is to prevent the block from being dragged down through the table. The normal force is trying to prevent this block from falling down through the table. Who is trying to drag the block down through the table? Well, the weight force is pulling down, trying to pull the block down through the table. Remember, that's the Earth's gravity. The Earth's gravity is trying to pull the block down through the table. The normal force exists to prevent the block from being pulled down through the table. So how big will the normal force be? The magnitude of the normal force will be whatever it takes to prevent the object from moving through the surface. The normal force will be as big as it takes to prevent the object from moving through the surface. So this normal force exists to cancel out the weight and prevent the object from being dragged down through the table. Well, notice the normal force is getting help with that job in this problem. In this problem, the y component of the tension is also pulling up and is also helping to oppose the weight. In this problem, the normal force and t sub y are cooperating together, so to speak, to cancel out the weight and prevent the block from being dragged down through the table. Since t sub y is canceling out a portion of the weight, the normal force can be less than the weight in magnitude and still cancel out that remaining portion. The normal force and t sub y together are canceling out the weight, so the normal force only has to cancel a portion of the weight. So it does make sense that the magnitude of the normal force came out to be less than the magnitude of the weight. If we had gotten a normal force that was equal to the weight or bigger than the weight, that would not make sense for this problem, and we would know we'd made a mistake. Remember I said earlier that when we filled out the force table, we should not try to figure out how the normal force will interact with the other forces. We should let Newton's second law figure that out for us. And now we can see that Newton's second law has figured that out for us and determined that the normal force can come out to be less than the weight in magnitude. You can see how Newton's second law figured that out for us, I think, here. So here we know that all the y forces have to cancel out to 0 in order for the object to remain vertically motionless. You can see that the normal force and the y component of the tension are cooperating to cancel out the the weight pulling in the negative direction. Since the normal force is getting help from t sub y, the normal force ends up only having to cancel a portion of the weight. So as I promised, we didn't have to figure out the relationship between the normal force and the other forces when we were filling out our force table, because the Newton's second law equation figured out that relationship for us. But then, after you get your result from Newton's second law, that is a good time to step back and ask why that makes sense. Now that we have this result, now is a good time to ask why this makes sense and to think about the relationships between the forces on our own to see why that result makes sense. Notice how that analysis was clearer when we thought in terms of components. To succeed in physics, think in terms of components. By thinking in terms of t sub y and t sub x, rather than the overall tension, it was clearer to see the interrelationships of these forces. So I hope this part of the forces handout now makes more sense to you. The purpose of the normal force is to prevent an object from moving through a solid surface. Therefore, the magnitude of the normal force will be whatever it takes in that particular problem to prevent the object from moving through the surface. But remember, you don't have to figure that out. You don't have to figure out what it will take to prevent the object from moving through the surface. You can just represent the magnitude of the normal force by little n in your force table, and then Newton's second law equations will figure out the value for little n. The Newton's second law equations will determine what it takes to prevent the object from moving through the surface. And then after you get that result, you can step back and ask why that makes sense. So the size of this answer does make sense, and that gives us confidence that we haven't made a mistake yet. So when you get results in your problems, even when you get results and answers, it's good to step back and ask, does your result make sense? Now, I know that that process that we just went through is actually quite challenging and difficult. It's not easy to go through this thought process, but I encourage you to practice it, because the more you practice, the better you'll get. And the advantage of asking whether your answer makes sense is that it will allow you to catch your mistakes. If your answer doesn't make sense, that might mean that you've made a mistake in your solution or your setup. And also, the process of asking whether your results make sense will help you to build deeper insight and understanding of the material. I hope that you feel that you have a deeper insight and understanding into the relationship between normal force and weight from the analysis that we went through here for understanding why the magnitude of the normal force came out to be less than the magnitude of the weight on this particular problem. We can see from this problem that we should not assume that n equals w. Now, there are many problems where the magnitude of the normal force does equal the magnitude of the weight. But there's also many problems where the magnitude of the normal force does not equal the magnitude of the weight, like this problem that we're working on right here. So don't assume that the magnitude of the normal force equals the magnitude of the weight. Just represent the magnitude of the normal force by little n in your force table, and then let the Newton's second law equations figure out for you what the relationship is between the magnitude of the normal force and the magnitude of the weight. Now we're ready to write our answer to part A. Remember that part A was asking for this symbol, which is the magnitude of the normal force. Well, we've determined the normal force has magnitude 16.4. And did you notice that my answer here is incorrect? What's wrong with what I wrote down? Well, if you don't include units, your answer is wrong. You must include units on your answer for the answer to be correct. Now, the question was also asking for the direction of the normal force, and that's something we'd already determined earlier in our solution. We decided the normal force was pointing up on this problem. So the direction of our normal force is up. By the way, in this video series, I'm not going to try to report the answers with the exact correct number of significant digits. Instead, I'll just use as many digits as seems comfortable and as seems like it will allow you to check your own answers against the answers that I'm getting. So we've completed this step. We used algebra to solve the y equation for Newton's second law, and then we were able to answer the question for part A. Now we should check that we've answered the right question and answered all parts of the question. Well, yes, part A really was asking for the magnitude and direction of the normal force. Do you see what it means to answer all parts of the question? A lot of students, I think, would answer this question as just 16.4 newtons. A lot of people would forget that there's also another part of the question asking for the direction. So make sure that you've answered all parts of the question. And of course, that also involves noticing that we still have to go on and answer part B in order to finish the problem. Check that your answer makes sense. We already went through that. We already saw that the sign here made sense and that the size of this magnitude makes sense. And remember, if we don't include units, our answer is wrong. Now, this check is not relevant for this problem. This is a check you would do on a symbolic answer, but for this problem, our answer was numeric. So we can skip this check. All right, well, now we've finished our solution for part A, and we need to move on to solve part B. Moving on to part B, remember that we should use a question mark to specify a specific symbol for the question. Well, the question is asking for the magnitude of the acceleration of the block. And remember, a good symbol for that would be A. This symbol stands for the complete acceleration, including its direction. This is the symbol for its magnitude. Now the question also asked for the direction of the acceleration. So here's how we can represent that part of the question. Now, in this part of the question, this would not be a good symbol because magnitudes don't have directions. Here we should use the arrow because it's only the complete vector acceleration that has a direction. So we went back and completed this step for part B. We wrote down a question mark and we wrote down a symbol or a combination of words in a symbol to identify the question. You should actually write down the question mark and actually write down exactly how you're identifying that question for each physics problem that you attack. Now, most of these other steps we don't need to recomplete because they've already been completed while we were solving part A. So we can just, I think, move all the way on down to using algebra now in our Newton's second law equations. We've finished working with the y equation, so now it's time to work with the x equation. Notice that the x equation does have this variable a sub x, and it should be clear that knowing a sub x will be helpful for figuring out what we need to know about the overall acceleration. And notice that this equation has one unknown. The only unknown in this equation is a sub x, so we're in good position to solve this equation for the unknown. We can simplify the left-hand side a bit to get 7.5 equals 3 a sub x. Now that equation is easy to solve. We divide both sides by 3. Do the division, 7.5 divided by 3. That's a division you might be able to do without the calculator, and we end up getting 2.5 as our result. Now that we've solved to a single number, we should put in the units. Since all the numbers we plugged in were in SI units, we can trust that this result comes out in SI units. And I hope you have memorized that the SI units for acceleration are meters per second squared. Let's pay attention to whether this result came out to be positive or negative. Well, mathematically, this came out to be positive. And remember my advice, you should include plus signs in front of positive components. So I'm going to put a plus sign in here to emphasize that mathematically this result came out to be positive. Does that make sense? Well, we'll discuss pretty soon why that makes sense. Notice how all our versions of the x component for Newton's second law are organized in this left-hand column, and all the versions of the y component for Newton's second law are organized in this right-hand column. And I encourage you to imitate that process when you work out the problems yourself. Arrange your versions of the x and y components for Newton's second law in two side-by-side columns. That's a way to keep your math organized. That's what I meant by this note in the handout. Set up the Newton's second law equations at the top of two adjacent columns. Then keep your later versions of the x and y equations organized in those two columns. That keeps your math from getting too messy. So I think we're ready now to answer the question. So notice we found a sub x. Technically, that's not what the question was asking us for. We found the x component of the acceleration here, and the question was asking about the overall acceleration. This wording implies that what they want to know is the magnitude and direction of the overall acceleration, not of a component. But it should be pretty easy here to make the link between a sub x and the overall acceleration. The question is asking about the overall acceleration, and we can use the components to figure out that overall acceleration. We know that a sub x is positive 2.5 meters per second squared from the work that we just did. And earlier we had determined that a sub y was 0. Earlier we figured out that a sub y is 0 because the object is motionless in the y component. And it should be easy to use these components to figure out what we need about the overall vector. When the y component here is 0, and when one of the components of the vector is 0, then the overall vector is basically identical to the non-zero component. So since the y component here is 0, our overall vector will have the same magnitude and direction as the non-zero component. So the magnitude of our x component was 2.5 meters per second squared. Therefore, the magnitude of the overall vector will be 2.5 meters per second squared. The direction of the x component was in the positive x direction, which was to the right, and therefore the direction of our overall vector will be to the right. When one component of a vector is 0, it's easy to figure out the overall vector, because the magnitude and direction of the overall vector will be the same as the magnitude and direction of the non-zero component. This is basically the same rule that we used earlier for breaking the weight and the normal force into components, because they both had one zero component. So now we've figured out the facts about the overall acceleration that the question was asking us for, and we can write down our answer to the question. By the way, remember we're including a plus sign here because it's a good idea to include plus signs in front of positive components. But we should not include a plus sign here. We don't include a plus sign here because this isn't a component. This is the magnitude of the overall vector. This is the magnitude of the overall vector, and remember, magnitudes can't be negative, so there's no need to emphasize when they're positive. Now here's the answer that we can write down for this question. The acceleration has magnitude 2.5 and direction to the right. Did you notice that I messed up? This answer is wrong because it left out the units. If you don't include your units, your answer is wrong. Remember that you need to memorize that the SI units for acceleration are meters per second squared, or you would not be able to include that part of this correct answer. Now, let's check whether this answer makes sense. Let's check whether this answer makes sense. And we can do that by drawing the acceleration vector. We'd already drawn the velocity vector earlier in the problem. So now we'll draw the acceleration vector. We've determined the direction of the acceleration is to the right. So here's an arrow pointing to the right. And remember, every vector arrow needs to be labeled. And the correct label for this vector is A. This should be an A with an arrow above it because this is indicating the direction of the complete vector. By the way, I mentioned earlier that you should not include the velocity vector in your free body diagram because the velocity vector is not a force. For the same reason, you should not include the acceleration vector in the free body diagram because acceleration is also not a force. You can see that by thinking about the units. The SI units for acceleration are meters per second squared, but the SI units for forces are newtons. And that demonstrates that acceleration is not a force. Don't include velocity and acceleration vectors in your free body diagram. Instead, it's helpful to write the velocity and acceleration arrows next to your main sketch, as we've done here. And we should ask now whether it makes sense that the velocity and acceleration are pointing to the right on this problem. How do you interpret this? If the velocity is to the right and the acceleration is to the right, how do you interpret that data? Remember that velocity and acceleration are difficult and subtle concepts to interpret, so we want to make sure we're using the correct rules. The direction of the velocity vector indicates the object's direction of motion. Since the velocity is pointing to the right, we know the block is moving to the right. Now, the acceleration is a subtle concept. The direction of the acceleration does not indicate the object's direction of motion. So how do we interpret that this acceleration is to the right? Well, we can use this rule. The acceleration in this problem is parallel to the velocity because they're both pointing in the same direction. And when acceleration and velocity are parallel, that means the object is moving with increasing speed. So the accelerate, we already knew the block was moving to the right, and now the acceleration tells us that the block is moving with increasing speed. The block is speeding up. Do you understand what I mean by parallel and anti-parallel? These vectors are parallel because they're both pointing in the same direction. Vectors would be anti-parallel if they were pointing in opposite directions. Now, does it make sense that this block is moving right with increasing speed? Well, I think we understood from the beginning that the block would be moving to the right, so the question is, does it make sense that it's moving with increasing speed to the right? Does it make sense that the acceleration is to the right? Well, here are some implications of Newton's first law that I hope you're familiar with from your course, and that can help us to understand why the rightward acceleration makes sense. So from Newton's first law, you should know that once an object begins moving in a certain direction, its natural tendency is to continue moving in that same direction, in a straight line at constant speed. Now in this problem, it seems that the block was already moving to the right when the problem began. So we don't need to explain why it continues moving to the right. Once it begins moving to the right, it has a natural tendency to continue moving to the right. However, remember that the natural tendency of the block would be to move at constant speed. So we do need to explain why the block is speeding up. There must be some force that explains why the block is speeding up. What is that force? Do you know what force is speeding the object up? Well, notice here that I've reproduced the version of the free body diagram where the tension is broken into components. And I think we can see from this that the reason that the object is speeding up is because of T sub x. The x component of the tension is pulling to the right, and that's what's speeding the object up as it moves to the right. Jessica is pulling on this rope. Part of that pull is pulling to the right, and that explains why the object is moving to the right with increasing speed. That's the force that explains why the object is speeding up in its rightward motion. So now we see that it does make sense that the object is accelerating to the right. Why is the acceleration to the right? Because of T sub x. The rightward portion of the pull on the rope explains why the object is accelerating to the right. So now we see that it does make sense that a sub x came out to be positive. It makes sense that a sub x came out to point in the positive direction because T sub x is pulling the box in that positive direction. If a sub x had come out to be negative, we would know, if a sub x had come out to be negative, we would know we'd made a mistake because there's nothing pulling the box to the left, so there's no reason why it should have an acceleration to the left. So we've seen that it does make sense that a sub x came out to be positive. How about the size of this number? Does the size of this number, 2.5 meters per second squared, is there any way to check whether the size of that answer makes sense? And I would say not particularly. Earlier in this problem, we saw that it was helpful to compare the magnitude of the normal force to the magnitude of the weight, because logically it wouldn't make sense for the magnitude of the normal force on this problem to have come out to be greater than the magnitude of the weight. But there's no similar comparison that's useful to make for this particular problem for the size of a sub x. Let's use this version of the free body diagram now to summarize the roles that each of these forces is playing in the motion of the object. What role is T sub x playing in the motion? Well, T sub x is what's causing the rightward acceleration. T sub x is what's causing the block to speed up. What role is the weight playing? Well, the weight is trying to start the block moving down through the table. The weight is trying to drag the block down through the table. But we know that the weight is not going to succeed at that because the weight is going to be canceled out by the cooperation between the normal force and T sub y. The normal force and T sub y together are cooperating to cancel out the weight and prevent the block from being dragged down through the surface of the table. So as a result, the block remains vertically motionless. Remember that T sub y and T sub x are the components of the pull on the rope. So because Jessica is pulling rightward on the rope, the block is accelerating to the right. And because Jessica is also pulling partially upwards on the rope, that helps to cooperate with the normal force to cancel out the weight. So notice that as we finished this problem and as we got an answer, we took the time to ask whether this answer made sense, and we thought through all the interrelationships of all these forces and how they created the motion of the object. But remember that you should leave that thought process for the end of the problem, not for the beginning of the problem. Remember that when we were drawing the force table in this problem, we did not try to puzzle out the interrelationships between the forces or how the forces were affecting the object's motion. We just thought about each force separately. Own terms, and we just represented the magnitude of the normal force by this symbol little n. We let the Newton's second law equations figure out for us what the relationships between the forces were and how the forces were going to affect the motion. For example, notice here that the x version of Newton's second law saw that there was a single x force in the positive direction. And that's why Newton's second law concluded that the acceleration in the x direction was positive. We let Newton's second law figure that out for us. But then once we had finished the problem, that was a good time to step back and to think about how the forces interrelate and how they affect the object's motion, so that we can check whether our answer makes sense and so that we can build a deeper insight and understanding into the physics concepts. So for part B, we've completed this step. We used algebra to solve, and we've also completed these checks. We checked that we answered the right question and we answered all parts of the question, or let's check that right now. So part B was asking for magnitude and direction of the acceleration, and that is what we answered. So what I mean by checking that you answered all parts of the question is many students here would just say that the acceleration was 2.5 meters per second squared and would forget that the question was asking for the direction. So check to make sure that you've answered all parts of the question. We've checked that our answer makes sense. Make sure that your answer includes units. Again, this check is not relevant because this check is for symbolic answers, and our answer on this problem was numeric. Now that we've completed our solution to the problem, let's step back and ask what we've learned about how to solve Newton's second law problems and how you can apply these ideas to solving other Newton's second law problems. First of all, I encourage you to attack these problems systematically. So try to make sure that you're actually following the steps from this Newton's second law handout. And in particular, try to solve the problem in three main phases: free body diagram, force table, and Newton's second law equations. Also, I encourage you to model your scratch work and notation on the scratch work and notation that I've used in this video. So, for example, try to draw a free body diagram that looks like the free body diagram that I drew here. Neat and clean and easily legible. Try to draw a force table that looks like the force table that I've drawn here. Neat and clean and easily legible. And then try to organize your Newton's second law equations the way I've organized them here. Notice that we kept all the versions of the x equation in the left-hand column and all the versions of the y equation in the right-hand column. So I encourage you to follow that pattern. Keep the x equation versions on the left and the y equation versions on the right, and that will help you to keep your mathematics organized. In this video, I tried to keep all my scratch work as neat and clean and organized as possible, and you should try to imitate that practice in your own scratch work. What are the most common mistakes that students would make on this problem, and how can you avoid those mistakes? One common mistake would be to forget to use this negative sign when plugging in w sub y. You have to plug in this, include this negative sign for w sub y. Well, you can avoid that mistake by making an organized force table where you put a plus sign in front of all your positive components. That will help you to remember to notice when you need a negative sign in front of the negative components. Another common mistake is notice that the problem gave us a tension of 15 newtons. The problem gave us this number 15 newtons for the tension. And a common student mistake is to try to plug that number of 15 newtons into the Newton's second law equations. But notice that that's not correct. We should never plug the 15 newtons into the Newton's second law equations because this is an overall magnitude and we need the components for the equations. So you can avoid that mistake again by making an organized force table where you separate the overall magnitude from the components, and then clearly label your Newton's second law equations so that you can see that this equation, for example, requires the x component of the tension, and this equation, for example, requires the y component of the tension. We never plugged this number 15 newtons directly into either Newton's second law equation. That would be a common student mistake. A third common mistake is that oftentimes students don't realize that they can plug in 0 for a sub y. The problem never mentioned that number 0 for acceleration, but remember we could figure out that because the object is vertically motionless, we know that the vertical acceleration is 0. So remember that if an object is motionless in a component, then that component of its acceleration is 0. Here are some more principles that you should try to imitate when you're solving problems. To succeed in physics, think in terms of components. I hope you saw how crucial the components were in solving this problem. For example, remember that our analysis for a sub x was completely different from our analysis for a sub y. A sub y was 0, and a sub x was an unknown that we had to figure out. So we had to think about a sub x separately from a sub y. That was a great example of the importance of thinking in terms of components. I've also already mentioned another example of the importance of thinking in terms of components, which is again this number for the tension, 15 newtons. Remember again that we never plugged this number 15 newtons directly into either of the Newton's second law equations because it represents an overall vector. That, of course, that doesn't mean that we ignored the 15 newtons. What we did is we broke the 15 newtons into components, and then we plugged the components into the Newton's second law equations. So that's another excellent example of the fact that to succeed in physics, we have to think in terms of components. If you're given information about an overall vector, you probably have to break that vector into components before you can plug it into your equations. This 15 newtons was information about the overall tension force, and we had to break that 15 newtons into components before we had numbers that we could plug in to our Newton's second law equations. And of course, when we were asking whether our answers made sense, we saw how useful it was to think in terms of components using a version of the free body diagram that showed the components of the tension force. For understanding these interrelationships, it was much more useful to focus on T sub x and T sub y rather than on the overall tension. That's another great example of how we succeed in physics by thinking in terms of components. Most students are very poor at that because notice, where did this problem mention components? Where did the problem tell you to use components? The problem never mentioned components or gave any hint that the key to the solution was thinking in terms of components. You're just expected to know that the key to solving many physics problems is to think in terms of components. So you need to get into that habit. I've mentioned always try to use the exact right symbols, including the exact right subscripts. Again, model your scratch work on the scratch work that I'm demonstrating in the video and try to use the same symbols that I'm using. Again, it would be useless here to call this A or this A because we had to treat A sub x completely differently from A sub y. So make sure you include the right subscripts so that you can think in terms of components. We've also seen that it really helps to have separate symbols for magnitudes. Remember that these are the symbols for the magnitudes of these overall vectors, whereas these symbols with the arrows represent the complete vector, including its direction. Try to imitate that use of symbols in your own work. Here's something I haven't mentioned. Try not to use the word it when you're thinking about a number or concept. Instead, always give a label for that concept in terms of a name or a symbol. So again, don't say that it is 0 or that it is 2.5 meters per second squared. Instead, say that a sub y is 0 or a sub x is positive 2.5 meters per second squared. Give the label to what you're thinking about. Or give them names. Say that the y component of acceleration is 0 and the x component of acceleration is 2.5. Don't say that it's 15 newtons or it's 7.5 newtons or it's 13 newtons. Again, give these labels. Say that the overall magnitude of the tension is 15 newtons or T equals 15 newtons. Say that T sub x equals positive 7.5 newtons, or say that the x component of the tension equals 7.5 newtons. By using a specific name or symbol, you're forcing yourself to clarify your thoughts. One of the most common mistakes that students make in physics is having the concepts blur together in their heads so that people use the wrong concept in the wrong part of the solution. To avoid the concepts blurring together in your head, to make sure you're using the right concept at each part of your solution, try to avoid using the word it. Not just if you're discussing the problem with somebody else, but try to avoid using the word it in your own mental thought processes while you're solving the problem. Force yourself to give each concept a precise label for what it represents. And again, maybe the simplest way to do that is to figure out the precise symbol. Because the names of the concepts can sometimes be rather long. It might be shorter just to identify the correct symbol for the concept. I tried to follow this principle during this video, and I tried to avoid using the word it and to give the label for each concept I was discussing as best I could remember during the video. Now, it took me a long time to go through the explanation for this problem. Obviously, your goal should be to eventually be able to solve problems much faster than that. But the reason this took a long time was because I was trying to carefully explain each step. I hope that you can see that with practice, you could execute these steps much more quickly than at the time that it took me to explain all the steps. On the other hand, remember that right now you're a beginner. So right now, your goal should not be to try to get the problems right as quickly as possible. Right now, you should be willing to take your time when you're solving these problems, because your goal should be to learn this systematic process and to learn the systematic techniques for solving Newton's second law problems and to build good habits and good notation for attacking these questions. So right now, take your time when you're attacking Newton's second law problems. You can worry about speeding up once you feel that you understand the basic process more confidently. So when you try the next problems in this series, I hope that you'll take your time and try to imitate the steps that I used for this problem. Try to use the same approach, the same notation, the same type of scratch work, the same steps that we used on this problem in the remaining problems in this video series. Okay, so what should you do now? Well, now you can move on to the next problem in this series. Remember, you can find the next problem in the problems document, or you can find it in the next video. On the other hand, if you were really bewildered by this problem and you didn't really have much of a clue about how to solve the problem originally, then I would actually recommend that you just redo this same problem, first of all. If this problem was extremely challenging for you, then now would be a good time to just try this problem again from scratch to make sure that you've really internalized the methods that we've talked about. But anyway, after you feel that you've internalized the methods from this video, that would be a good time then to move on to the next problem in this series and to continue practicing the systematic approach to Newton's second law problems that we introduced in this first video. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.